Now let's discover the latest advancements in virtual ride quality assessment with Multimatic and Michelin. Engineers Michael Caradonna, Tony Yardley, and Behzad Danaei present their collaborative effort in parameterizing Cosin's advanced FTire model for VI Grade's Gridmesh road model. Learn how this innovative approach enables subjective assessment of vehicle ride performance, enhancing factors like comfort and stability.
Thank you. Good afternoon, ladies and gentlemen. This afternoon we're going to be talking fairly briefly about one specific key part of the essential process of being able to predict secondary ride. We're going to be very focused on one particular aspect. First of all, I'd like to really acknowledge everybody's involvement. This is the involvement from 3 separate companies, Cosin, Michelin. Gary and Matthew Pearson were co-authors of the paper, but they couldn't be here. Behzad, Aidan, and Peter from Multimatic as well. Not sure Michelin really needs much introduction. They are one of the industry leaders in the field of tire manufacturers and have a very advanced simulation capability, both structurally and in terms of dynamics as well for the tire performance. Multimatic, just a brief introduction. The company is based in Toronto, Canada. We're a medium-sized company that is a tier 1 supplier to many manufacturers throughout the industry. That's the kind of the business base, and then Michael, myself, Behzad, we work in Multimatic engineering, which really facilitates the development of our products. We tend to be very focused on the performance vehicle side, so we'll be talking specifically about high-performance vehicle in this presentation. But this kind of section of Multimatic specializes in damper technology, active and adaptive dampers, which have been released into production quite recently. So in terms of the project scope, we're going to focus on one vehicle, which Michael will detail. But we take, with Michelin's integral involvement, one of their highest performing road tires, and with them develop it specifically in a bespoke manner for the Mustang GTD supercar, I guess, would be the best way to describe it. Then we're going to show how we used Cosin's FTire to predict some of the critical accelerations and forces going into the body structure that's going to be necessary in our ability to evaluate secondary ride and NVH. We'll detail how that FTire model is populated, and then on the bottom row, we'll be looking at how the vehicle, the real vehicle, was instrumented so that we could validate this process. We'll go on to essentially present the key results. So without my further waffling, I'll continue. So I'm not sure FTire really needs that much introduction. I think most people will be familiar with it. But in comparison to a single point follower tire model, which is on the left-hand side of the screen, it has a distributed contact patch with a structural belt model. The important thing for us is that it runs in real time, on the DIM 250 simulator that we have in Irvine, Michigan. What you see here in the presentation is a slide that I essentially stole from Cosin. It's their slide. But the way that the point follower tire on the left, the 4 spikes as it goes over the sharp object, is unrealistic. FTire models the way that the tire envelops the different contours of the road. Bit more detail about FTire. When we're running FTire in real time, we essentially break the tire down into a series of smaller chunks. We run at the lower end of the segment. I think it was 60 segments around the belt. And ideally, we'd like to run more. As the computing improves, we would run more and get higher fidelity, and we'll see it where we are actually trading off a little bit of NVH performance. The process that Michelin went through, it's kind of interesting. Cosin specify how to characterize their and populate their model. So there's basically a series of lab measurements of the tire, in-lab measurements, and in addition with an FEA model, structural model, that comes together into one single FTire format model that can be used actually for many things. One of the advantages of FTire is that you have a single model and it is applicable in many different situations. We're only using a fraction of its potential in this presentation. What I've done to kind of save time is put the measurements and the results in together. The legends are extremely small, but the blue line is the measurement, and the red line, which is often directly underneath, is the FTire model performance. Shown here is kind of the structural performance of the loaded and unloaded radius versus speed, how it varies versus speed. I think it's an extremely good fit. The one plot where it doesn't match, Gary told me isn't actually, that's generic data from the brochure. He didn't have that plot available. So that one is the one that looks like it doesn't correlate very well, and it's because it's not real data. Getting on to the more dynamic events, using a belt with a cleat, the tire rolls over, and from that, a longitudinal stiffness, and also by skewing the tire, a lateral stiffness of the tire is modeled. And here, again, the comparison, blue is measured, and red is the FTire model. I think the fit is, I'd say, a work in progress. The bottom left plot is a vertical stiffness as it pinches against the rim on a very high load. And then the bottom right plot is from a static steering test, showing a significant hysteresis loop that is reasonably well reproduced. Probably the most crucial characteristics for us are the transient vertical responses of the tire. And again, this is done by driving over a cleat object. Let me explain some of the plots. The gray section is where the tire is actually in contact with the cleat. And then, again, the blue is measured. The red is the FTire model. Far left is the vertical load. In the middle top is the PSD of that vertical load characteristic, so looking at it across the frequency range. And then far right is the longitudinal force, again, as it goes over the cleat. Interestingly, that I was surprised how long the longitudinal force still fluctuates after you've gone over the cleat. That was kind of surprising to me. And then lower down in the bottom, we have the longitudinal force PSD. The one interesting thing to note here is that in the top middle plot, the scale is really hard to read, and I apologize for that. These were taken straight from a printed report. But the blue and the red match reasonably well up to 150 hertz and then start to diverge. And that diversion is, for our presentation, actually outside the range. But for applications such as Charlie's and Bentley's, it's going to be crucial as well. The contact patch is specifically modeled with FTire, and the model fit, it's actually quite hard to see the outlines. The black is the actual measured contact patch, and then blue and red is again measured and F-tire. The blue basically outlines the black area, and then you may be able to see the red. The basic picture here was that at low speed, the match is really very good, and then as the speed increases, the difficulty of matching that contact patch increases considerably, because the time that the contact patch is actually touching the ground is very short. And that relates back to our 60 segments in the belt. If we could have more segments, we would be able to reproduce it to a higher speed. And then probably near and dear to driving enthusiasts' heart is the lateral force and aligning moment characteristics that affect on-tent steering and performance driving. Here we see good side force reproduction, but in the middle plot, the aligning torque is significantly lower in the F-tire model than we see in the measured data. Again, blue is measured and red is the F-tire model. We understand that this was a direct trade-off between matching the NVH characteristics and being able to develop the full aligning torque. I wasn't involved in that process directly, but I know Benny sat over on my left, which greatly appreciate all the input he's helped us with, would be able to discuss those at length, I think. And then we've basically seen the aligning torque during steer on the top left, and the longitudinal force is also a pretty good match. What's the comment there? Oscillation in the model around high braking forces. We did see some oscillation, again, kind of in the contact patch frequency behavior, contact patch behavior around that frequency. So that is an area that we'd like to refine. We probably need more compute capacity to do that. I'm going to hand over to Michael now, and he will detail some of the full vehicle information.
Yep, so this is a slightly more exciting topic. As you can see, this is the car we're testing this all on. It's a Ford GT prototype, or Ford GTD prototype. One of the big complex parts is the inboard rear suspension, which added a lot of pre-processing and post-processing to all of the data. It's also equipped with our ASV, Multimatic's ASV and DHR system, dual height rate and adaptive spool valve. In addition to that, it has absolutely monstrous tires with a 325 front and a 345 rear. Those tires are Pilot Sport Cup 2Rs, as we were talking about before, kind of the best in class for on-road performance, but also on the racetrack. Very good, very sticky. So how we set up the loggers. Each damper had a 1,000 hertz three-axis accelerometer mounted straight to the damper, which on the rear is not in line with the hub, so that took a little bit of post-processing to fix. And there was also a 200 hertz three-axis accelerometer mounted basically right behind the center console, which is also a gyro. So you might be wondering, what kind of road are we driving this on virtually? And the digital twin in real life. So it's a Michigan ride road. It's normally a really bad Michigan road. Has a lot of big concrete patches. They create a lot of secondary shake. As you can see here, we've modeled it twice. Once as a road mesh, once as a grid mesh. It's a little hard to see, but the grid mesh is a much finer density, 10 centimeters mesh spacing, which compared to a classic road mesh being essentially double that, is very high density, and that would more accurately reproduce the shake that we were experiencing in real life. This is all generated from a point cloud scan, as you can see in the left here, and the location of the road, and also some close-ups of the sections that create a lot of the shake. It's kind of the buckling of the concrete slabs create a lot of those really aggressive shake motions. So our cockpit, as you can see, and as you may know, a lot of the VI grade simulators have cut car cockpits. Well, with our needs being to switch between a Mercedes C200 to a Ford GT to a Ford GTD, we can't just have a cut car because we'd be swapping cockpits all the time. So we have a fully modular cockpit. Right now it's set up in the Ford GT Mark II configuration, but within 2 or 3 hours we can switch that to a C200 or some LMP2 car otherwise, which has been a very big step for us to be able to include all of our potential development opportunities. So to run this real time, it was a little bit of a challenge for us. Here's a little bit of our computer specifications. So the biggest addition to running it real time was to have one core dedicated per tire. Nothing else on that core. Each core has its own tire. And then some FTire settings pointed at by Cosin, run it in real-time mode. And then we ended up reducing the number of tire states from 30 to 15. That step was the final straw in being able to run it real-time. So I'll hand it back over to Tony to talk through some of the results.
Yep, thank you. So really just to close out, I've got 2 more slides. I am going to go through them in some detail. So I hope you're all brushed up on your frequency domain analysis. A show of hands, everybody good? Yes, thank you. So what we're looking at here is the response of that IMU, or the motion of the vehicle body as a whole, and in 3 directions: vertical at the CG, roll, side to side, rotation, and pitch, front to rear rotation. As usual, blue is measured, and red is the FTire reconstruction and simulation, run on the DIM 250. The CG vertical, which is the major component in what the driver feels going into the seat. So this is essentially an analogous to the seat track input, is actually really well matched through the whole frequency range. We're working from 1 to 100 hertz in this plot. I'd say it's a really good match up until maybe 50 hertz when it starts to diverge. And the amplitude of the PSD, which is the spectral content, is so low at that point that we can accept some divergence. Roll isn't quite so well matched. Here we see a bit more roll response, around 10 hertz with the peak roll response of the car. It's an incredibly stiff car on an incredibly abusive road for such a high-performance car, but it was what we had available to drive on as a representative road surface. We're basically following it as a trend, and then again, divergence at 50 hertz and above is interesting. And the last plot on the left is vehicle pitch, so front to rear rotational accelerations. And the one place where it really significantly diverges is right around 10 hertz, right in the center of the plot. That's a significant deviation, and we have to chase that one down. It's a bit too low for it to be flexibility in the mounting of the IMU. I tend to suspect something to do with phasing of the wheel hops modes, because they're right around 10 hertz. But we'll see on the next plot some of the frequency content that's coming into the car. So this is kind of what the driver would perceive. So I think we're doing an excellent job for a rigid body simulation at this point. And then the last slide is basically what the FTire is generating as forces, the dominant forces into the wheels and suspension. And I think the first two plots are the front left and the front right. They're a good shape match. There's a little mismatch in the frequency. The peak frequency is just over 10 hertz, 10 to 15 hertz. We are a bit lower in FTire, so it probably means we have a bit too much mass associated with the front and unsprung suspension in the front compared with the real car. And then the rear is a really good match. It's a little off at the very low frequency, 1 hertz. That's much more to do with our suspension model. We haven't had a chance to correlate the suspension unit on our 4-post rig, which we'll come to in next steps. But probably the most interesting point from a tire modeling perspective, which is the FTire involvement, is right out near 100 hertz. It's actually 85 hertz. There's a big red spike, which is the FTire model, just in the rear tire, is showing a large response, or basically a resonance. And we understand that to be a slightly underdamped contact patch mode. And talking with our colleagues in China who did the correlation work, they were actually aware of that during the correlation, but traded that off against some of the other issues. So they went in favor of matching some of the static stiffnesses. What we're going to do is go around in another correlation loop now that we have this data to look at and see what is the most important aspect to keep to focus on during the correlation. So just to wrap up, our next steps are essentially continue development of the FTire model. We have a trade-off between the MVH behavior and some of the other behaviors. Version 2, which I understand is coming in July, would be the next improvement in the FTire model when no trade-offs are necessary. Now that we have this information, we can do a more focused job of knowing which characteristics we need to match during correlation of the tire model. Then from a vehicle side, we would be using our traditional 4-post test machine, essentially a lab test for the full vehicle, to correlate the suspension, particularly the friction, which is a tricky thing to know ahead of time, which is why it's not particularly well accounted for in in our full vehicle model at the moment. And we like better instrumentation. We only had the car for 3 hours. It was the first prototype to get in thin on the ground. We only had it for 3 hours, and it was shipped off back to Canada. We do a greater variety of surfaces that would include enveloping characteristics of the tire. And when we have all that in place, we'll be back on the DIM with a subjective comparison between on-road performance and off-road. So that's pretty much the end of our next steps. And that brings us to the end of the presentation. If there's any questions, we'd love to pass you over to Cosin. No, seriously, we can answer any questions if there are any questions. No? Thank you for the time.
Thank you.
Oh, we have one question. Can we have a mic?
Hello, Enrico Maria Talarico from Bugatti Rimac. I have a question actually on the correlation plots you showed about both body motion and wheel hub accelerations. Are you also planning to instrument the cockpit of DIM 250 to understand if those correlation also applies to what really felt on the DIM, or at the moment you're just focused on model correlation?
This stage has definitely been focused on model correlation, and it's a great question. We have a DIM FSS in our future, which will make the whole matching up to 100 hertz become much more relevant. At the moment, we think we've got a bandwidth of about 30 hertz. So I think we've got enough to capture up to the middle of our normal secondary ride range. We don't capture tactile harshness influences at the moment, but that's coming with the FSS. Yeah, FSS. Yeah, thank you for the question. That was good.
Thank you.
Yeah. Any other questions? We have one over here.
Thank you for the presentation. I'm Kevin from RF Pro. You mentioned the Gridmesh in one of your slides, that it has a resolution of 1 centimeter.
Yes.
Does it also apply for a vertical axis, or just?
Oh no, that's the spacing of the lateral and longitudinal spacing of the points.
Yeah.
The vertical resolution is in the microns.
Microns. Okay.
Yes. I think there's more noise in the measurement system. But we retain information down to the micron. There is a modest amount of filtering that needs to be done on a typical LiDAR scan that we receive. But as we go to more and more contact patch points, that becomes less and less necessary.
Thanks.
Yeah, good question. Thank you. Any more questions? One last one. Thank you.
Tony, so you're using FTire, so a higher order tire model.
Yeah.
What modeling elements did you use for dampers and bushings?
We essentially used our current status of car real time. Sorry if that wasn't really clear. The bushings are essentially incorporated into the suspension characteristics. We correlate KNC test response of the suspension, and those are the characteristics that we put into the car real time. So it is a good question. As you go up in frequency range, you certainly need to consider the dynamic performance of those bushings. An improvement in body modeling and suspension dynamics might be necessary in the future. Yeah, thank you. Okay, I think we've run well over time, but thank you for your time.